Okay, section 6. We're going to start looking at some other things which you saw previously. In Math 95 or somewhere in your previous history, you should have run across rational expressions. Rational expressions are fractions that have polynomials. And polynomials, have to meet certain requirements. A polynomial, the exponents must be positive integers. Can't have fractional exponents, can't have negative exponents in a polynomial. So rational expressions are made up of a polynomial divided by a polynomial. Here's an example. And actually every fraction in all number fractions, every kind of fraction is really a rational expression. Normally you don't use the term rational expression if all you're talking about is a fraction. You just say a fraction. There's nothing special that needs to happen if you're working with a rational expression where your denominator is a number, that it does not have a variable in it. So those types of rational expressions don't require anything special. So I'm going to limit myself to working with rational expressions where there's a variable in the denominator. That's where something additional must take place, besides just the normal calculations. So here's a rational expression. Here's another one. This is a much more involved one, but it's still a polynomial divided by a polynomial. That also, but you wouldn't have to do anything special for 3 halves. As with all things in math, you cannot divide by 0. That is an undefined situation. When you have a variable in a denominator, variables take on different values. That's the whole purpose of having a variable, is because it can have different values. In order to prevent division by 0, we must ensure that we don't put a value of x in that would cause the denominator to equal 0. This limitation on x is going to affect how we solve equations. And we need to be conscious of what values will make these denominators 0. If you're looking at a rational expression like this one, if you let x equal 0, you'd be dividing by 0, right? So we can't let x equal 0 in this expression. Otherwise, we'd have an undefined situation. Over here, x equals 0 is no problem. But there would be some other value that would be a problem. So we have to ensure we don't have values of x which cause the denominator to be 0. For this one, we can't let x equal -2 or +1. Either one of those will make this denominator 0. So those are values that are not allowed. Where that's going to affect us is when we start having equations that have these rational expressions in them. If we come up with a solution for this that had these two values, we'd have to throw those values away and say there's no solution. So that does affect when we're working problems, solving equations. We need to be conscious of that requirement, that the denominator cannot be 0. Here, no variable, so all values of x are fine there because there really aren't any values of x there. All right, let's look at a rational equation. The rational equation is just an equation that has a rational expression in it. So nothing strange. The tools you use to solve a rational equation are exactly what you used already. Nothing new. Same set of tools. There's one additional requirement Maybe I should say there are 2 additional requirements. One of the additional requirements is that you cannot allow value of x, which makes the denominator 0. We just looked at it. That's one of the requirements. None of your solutions can make a denominator 0. The second requirement is when you're trying to solve that equation, you must get rid of your fractions. Because you have variables in the denominators, a solution to an equation cannot have variables in a denominator. So you have to get rid of denominators. It's not anything new to get rid of fractions. It's just a requirement that you do so. If you don't have variables in a denominator, you just have normal fractions, you can work with fractions as long as they're number fractions. No problem. But if you have variables in those denominators, you cannot keep them. You have to bring those variables up into the numerator. Get the variables out of the denominator. So in other words, eliminate all denominators. So eliminate fractions and checking your answer. Checking your answer is where you check for that division by 0. There are actually 2 ways you can do that check. You can either establish beforehand what values to throw away by looking at your denominators, or you can wait, solve the equation, then go back and compare your answers. Try your answers to see if they make the denominator 0. I usually do the latter. I get my solutions and then see if they cause a problem. So undefined, if a denominator is 0, you throw those solutions away. Here's a rational equation. I want to get x equals, which means I cannot have x's in the denominators. In order to get rid of the denominators, what I have to do is I have to find a common denominator for the entire equation. I then multiply everything in the equation by that common denominator. That will allow me to divide out the denominators and leave me with denominators of 1. That's what I'm trying to get. Once I have that situation, I solve that equation. Then I check my answers to see if they cause a problem. So, first thing I have to do is find a common denominator for this equation. When you're working with rational expressions, the way you find a common denominator is like you find a common denominator for numbers, except you have to do it with polynomials. And that's why, if you were in some of my earlier classes, I stressed learning to find common denominators for fractions in a certain way, because you need it here. With polynomials, you want the least common denominator, otherwise you're going to be working with something unmanageable. So you need to find the smallest polynomial combination, which includes all of your denominators. The way you do that is you factor every denominator. So every one of those polynomials in the denominator we need to factor. Well, this first one, no factoring required, because it's already x to the first power. No factoring required, x to the first power. This one needs to be factored because it has x above the first power. What's the factoring of this one? What would you get if you factored this? Yeah, it's just x times x minus 3, isn't it? Which is the same 2 factors as here. When I find the least common denominator, what I want to do is I want to take this first denominator, all of its factors. Then I want to look at the next denominator and see if that factor is already included. When you're doing that, remember, x minus 3 is the factor. X minus 3 is not the same thing as x. So if I have this, I do not have that as a factor. That's a term inside a factor. So I do not have this represented if all I have is x minus 3. So I need this denominator, and then from here I also need this factor. So I need x minus 3 and I need x. as factors in my least common denominator. Then over here, I would need x, which I already have, so I don't need it a second time. I would also need x minus 3, which I already have, so I don't need it a second time. Therefore, my LCD is x times x minus 3. What I now have to do is I need to take that LCD and multiply it times this fraction, times that fraction, and times that fraction. So x times x minus 3 times this, x times x minus 3 times this, and x times x minus 3 times that. I can divide out common factors now. In this first one, the x minus 3 is common. Divides out, leaves me a 1 in the denominator, right? And a 1 up here. Over here, the x's divide out. Over here, the x's divide out, and the x minus 3 divide out. Now my denominators are all 1. So I multiply together what remains in my numerators, x times 1 times x minus 5. And I'm going to clean this up. Oh, okay, so I did it. So I have x times x minus 5. I have x minus 3 times 1. And I have 1 times 1 times minus 7. And now I have a normal equation. No denominators. Actually, I got rid of all my denominators are 1. I don't have any fractions. I got rid of the number fractions as well as everything else. And that's normally what you're going to do. If you're going to get rid of a part of the fractions, might as well get rid of all of them. And then you're just working with whole numbers. So I solved this equation. In this case, it's going to be a quadratic equation. And you choose whatever you think is the best way to solve it. If you notice, this will factor. So you get the solution, and you get the same number twice. That's okay. I mean, that's just a repeated root. Normal thing. Nothing wrong with it. But those are your solutions. At this point, what I would need to do, because of the way I worked it, I need to take these two values and go back to my original equation here. Here's my original equation. My two numbers were 2 and 2, right? I need to plug 2 in here and see if that causes this to become 0. If I put 2 there, 2 minus 3, that's not equal to 0, is it? 2 is not equal to 0, so that's not 0. 2 times 2 minus 3, that's not equal to 0. 2 does not cause a problem, therefore I can keep those solutions. So the solutions to this equation are x equals 2 and x equals 2. The other way was the way I showed it on the slide, where once I had factored my denominators, I set each factor equal to 0 and see what values that gives me. So I cannot allow 3 and I cannot allow 0 as answers. So if I know that 3 and 0 are not allowed, once I get my answers over here, neither of those is 3 or 0, so I can keep those answers. Two different ways to do the same thing. But the procedure, rational equation, find the LCD for the entire equation. Multiply the equation, both sides, by that LCD in order to get rid of all your fractions. Then solve the equation, check your answers back against the denominators. If you want to check the answers completely, that's fine. It's a good idea. But as a minimum, you must check it against the denominators. You don't have any choice there. Because there are cases where you throw away answers. I don't know if I don't think I have an example here, but there are cases where the equation will be, you'll get answers and then you go back and you have to throw answers away. There are even situations where you have to throw all the answers away, and so you have no solution to the equation. You can go through the solution process and you'll get numbers, but you can't allow them because they would cause division by 0. Okay, so another example. If we're going to work this, we need to get rid of the fractions. So how would I get rid of the fractions in this equation? What's the LCD for this one? Right, that 2 is part of it, because I want to get rid of the 2 also, right? So I want 2 times x plus 1. That's my LCD. So what do I do with that? Times what? This one? Every one of them. So multiply it times every one of them. And remember, anytime you're doing this sort of thing, look to see if you can divide out common factors. That's the whole purpose for doing this case, is to divide out the common factors. And sometimes you don't have any fractions. This side isn't even a fraction, so that's just going to become an expression. Then okay, we get that. Now what? Give up because it's too long? What do you do here? Solve the equation. I mean, combine like terms. Get everything on the same side. Combine like terms. You know, it looks like a quadratic, but guess what happens? Here's an x squared term. Here's my only other x squared term. What happens when I subtract that from both sides? They cancel, and I don't have a quadratic anymore, do I? If you go through all of that and solve, you get that number. All right, are we finished though? There's one more step we must do. No option. What's that last step? Take that number and check it back up here. Does it cause division by 0? Where's the only place I have to plug it in? That's the only required place. If I want to check the whole thing, then that's certainly okay. But I'm required to check it here. If I plug 3/7 in there, is 3/7 plus 1 equal to 0? No. So I can keep the answer of 3/7. So that's the solution to that equation. Same set of steps that you use on any other equation. You add and subtract, multiply and divide both sides by the same thing. It's just that you're required to get rid of your fractions. You're required to check your answer. On the exams, it's possible what you would see is if you're given a rational equation to solve, you might see one of your 4 answers is both answers. One of them is one of the answers, but not the other one. The third one is the second one, not the first one. And the fourth one is none of them. And so if I were writing the problem, which I didn't write any of these problems in this test bank, I would make up a question like that, where it had, 2 solutions when you solve the equation. But then I'd pick some problems where I'd have to keep both answers, some where I'd throw one answer away, and maybe a couple where I'd throw all of them away. And therefore, if you just solve the equation, you might be picking the wrong answer, because the solution of the equation doesn't necessarily work. You have to check it back. So make certain you don't forget that last step. All right, so I think we've got time before class is over. What's the solution to that equation? Or solutions, maybe more than one. I'm sorry? Reduce, I mean, that's just the first step. I don't see any other thing it can be. It has to have this factor in it, and it has to have that factor. And don't multiply them together if that's what you're asking. Don't multiply them. Just leave them separate because you're going to want them separate anyway. But no, there's nothing to combine or simplify in there. Is that right? Did I get that right? Does anybody see the shortcut for this? There's a way you can do this without having to find the LCD. I don't expect anybody to see it, but what would you have to do to cross multiply? And let me preface that. In my opinion, there's only one place you cross multiply. It's across an equal sign. You never cross multiply anywhere else. So given that, rearrange this. And then cross multiply. You have two fractions. That's called a proportion if you have one fraction equals another fraction. You can solve a proportion by cross multiplication. So if you ever get an equation which has just two fractions and the other one's 0, then you can rearrange it until you have fraction equals fraction, and then you can cross multiply. If you cross multiply, you get that, which immediately gets you to that, which leads you further on. But that's not going to happen often, so don't count on being able to cross multiply. Because if this were anything other than 0, you can't do it. This one actually, the question, instead of being solve it, was what are the values that are not allowed? So these are not the solutions. We actually solved it. Let's go, if we solve this, well, no, I think it's the same thing. What solutions would not be allowed for this equation? X equals 3. Well, guess what? this one, if you solve that equation, you get 3. And so you have to throw that answer away. And you wind up getting no solution. Okay, before we move on to that, what I want to do is I want to have you practice a couple of equations. So let me put them up on the board. What I want you to do is I want you to solve that equation. What are the solutions to that equation? Remember, rational equation, you have to get rid of the denominators, put everything up into the numerator by finding a common denominator. Multiply the whole equation by that common denominator. And don't forget to check your answer. Anybody got an answer yet? Let's see. I don't know. I don't get -4. That's what I get is 4. So either I made an error or you made an error. Look at your signs. Make sure you didn't get a sign wrong somewhere. Or when you divided by the coefficient, did you divide by a -3 or did you just divide by 3? Signs are important. Okay, so solution of this is x equals 4, right? Wrong. What haven't I done yet? What happens when I plug it in? So what's my answer? No solution to that equation. I can't allow 4. 4 causes me to divide by 0, so I can't use it. So there is no solution to that equation. There's no value of x which will make that equation true. You have to do that last step. So, when you're solving it, obviously, watch your little errors that can cause problems, but then don't forget that check. Any questions about how this was worked? This is the process. Find your LCD. Remember, finding the LCD, you may have to factor denominators and pick factors. Use the smallest number of factors, the fewest number of factors that you can get by with. You need to have enough, but don't use more than you need. It's just like when you're getting common denominators for numbers. You can use a bigger number, but it makes your numbers you work with larger, and when you start simplifying, it may become more difficult to simplify. So if you can get by using the smallest one, in polynomials, it's even worse. You need to use the fewest number of factors to keep your polynomials as small as possible. So find your LCD, multiply the entire equation by that, solve the resulting equation, check your answer. Those are the steps you have to go through. Okay, another one. Am I doing okay so far? Okay. Now let me go straight here. You remember how'd y'all solve that? What technique? Quadratic equation? Okay. I didn't use quadratic equation, but hopefully I got the same answer you got. Yes. Mm-hmm. This one? 2 times x is 2x, 2 times 1 is 2. And then I had the 1 over here, and I subtracted the 1 from both sides. That gave me the 1 here. So is that what y'all got for x's? Okay. Here, grouping, factor by grouping. If you want to factor, if this coefficient is larger than 1, you take this number times that number. And then you'll want to find two numbers that multiply to give that and add to give that. Well, 4 and 1 multiply to give that. Do they add to give 5? Yes, they do. So the two numbers I want are 4 and 5. So I use 4 and 1. So I use 4 and 1 to break apart the 5 in order to give me 4 terms. Then with 4 terms, I group them by 2 and 2. Factor out the greatest common factor in the first 2, greatest common factor in the last 2. That leaves the parentheses or a common factor. So I'd factor out the parentheses, which leaves these. So those are factors I can set equal to 0 and solve. Look back, I'm not sure on this book. I think there's something in chapter R about factor by grouping. It's a much easier way to factor polynomials where that coefficient is larger than 1 than just trial and error. If you're not going to learn grouping, then you're going to be using quadratic formula. This one, I chose to try the factoring, and it turns out it works. So that's not always a wise choice. You may just want to go straight to the quadratic formula if you don't immediately see the factoring. When I was working this out yesterday, I just decided to try the factoring, and it turned out to work. Okay. Notice anything about these answers, though? They're both negative. Anything else? What type of equation do I have? What's it? A rational equation. What do you have to do when you're solving a rational equation? You absolutely must check your answers. What happens when you check your answers? That one causes division by 0. So the answer is only the x equals negative a fourth. Don't forget that step. Very important. And since I think I mentioned this, since I didn't write the test bank of questions, it might not be that way, but if I were writing it, I'd have a problem like this. I'd have one of the 4 choices be both answers. I'd have another choice be this answer, another choice be this answer, and a 4th choice be neither answer. And you definitely have to check to see. So it's important, because if you answered both of these, you just missed that problem. Rational equations, you will see them. You do need to know how to solve them. It's really, you're not doing anything different on how you solve any other equation, except you're required to get rid of fractions and you're required to check your answer. But other equations, you may get rid of fractions anyway, so that's not anything different. Frequently, if I have an equation with fractions, I'll choose to go ahead and get rid of them, even if they're number fractions, just because it's easier to work with whole numbers. And that's all we're doing here, is we're getting rid of those fractions. What about it? If I take negative 1 and I put it in here, what happens? And what does that mean? I can't divide by 0. So you have to throw away any of those x's that cause you to divide by 0. That one causes me to divide by 0, so I have to throw it away. That's rational equations.
Another type of equation that we need to look at is a radical equation. Radical equation is just an equation that has a radical in it. Here's an example of a radical equation. Notice that it has one radical. We could also have equations which have two radicals, possibly more. I don't think you will see any that have more than two radicals in them. The technique for solving radical equations. First, you isolate the radical. Isolate the radical means get the radical by itself on one side. You want all the other terms except that radical term to be on the other side of the equation. Once you have the equation and that's set up that way, you raise each side of the equation to the power equal to the index of the radical. Now remember, the index of the radical is the little number that goes in the notch of the radical symbol. When there's not one there, such as a square root, the number is assumed to be 2. So it'll be 2 or larger. It'll never be smaller than 2. If it's not showing it is a 2, any other index would have to show. Once you've isolated the radical in a radical equation, you look at that index and then raise both sides of the equation to that power. That will get rid of that radical. If you had more than one radical to begin with, it probably will only get rid of that one. You will still have the radicals, so you're going to repeat this process and isolate whatever radical remains and then raise both sides of the equation to that index. After you've done that, you will have no radicals in the equation. Solve the equation in the normal way. Now, because you have done this raising to power, you must check your answer. There is no option, because the process of raising the equation to a power can introduce solutions which do not work in the original equation. Previously, when you solved an equation, checking was optional just to see if you made any errors. For radical equations, just like for rational equations, you have no option. You must check your answers to be sure that they work. Let's look at an example. Here's an example that has only one radical in it. In order to solve this equation, what I need to do is isolate that radical. In order to isolate the radical, I have to get it by itself. The easiest way to do that is to add the radical to both sides of the equation. If I add square root of 3x plus 18 to both sides of the equation, then I will get x equals this. Now I have the radical isolated. My next step is to look at the index power, which is right here, and because there's no number there, it is a 2. I want to take that 2 and I want to raise both sides of the equation to the second power. I want to do that. And notice what I'm raising to the power is the radical. So I'm taking the radical and multiplying it by itself. The left-hand side is very simple in this case. When I perform this squaring in this equation, left side is x squared, the right side I'm squaring a square root. When you square a square root, what you get is just what's underneath the radical symbol. So on the right side, I just get 3x plus 18. Now that I have 3x plus 18, no radicals in the equation anymore, solve the equation with a normal technique. Move everything to the left side because it's a quadratic equation. So I need everything on one side, 0 on the other, and then apply whichever technique for solution to a quadratic you prefer. You may prefer the quadratic formula. It doesn't really matter as long as you choose something that works. So here I've put the equation in standard form, which is necessary. This one actually factors, and so I factored it to solve it. Two numbers that multiply together to give minus 18 and add to give minus 3 or minus 6 and plus 3. Now I set each factor that contains a variable equal to 0, solve those two equations, and I get two answers. X equals plus 6, x equals minus 3. Normally you would be finished at this point. However, this is a radical equation. It is not a normal equation, it's a radical equation. Therefore, when we get solutions, we must check each of those back in the original equation to make sure they work. Let's see what happens when we do that with these two solutions. Here's the original equation, and I'm going to do this side by side, do them in parallel. I'm going to put 6 in over here for x, and over here I'm putting the other solution, minus 3 in for x and minus 3 in for x. And so going down in parallel, doing the arithmetic here, and I get on the left side 6 minus 6, which does indeed equal 0. On the right hand side, notice though, I have a minus sign here, I have the minus in here, which gives me minus 9, which gives me plus 9 in here. When I take that square root, it gets a 3, but then there's a minus in front of it. So I have minus 3, which is minus 6. Minus 6 is not equal to 0. Therefore, I must throw away this solution. The only solution is x equals 6. This illustrates why you must check your answers once you have them. You can't just blindly accept them, you must check them. Now let's look at a different example, one where we have two radicals. The technique to solve a radical equation with two radicals is exactly like the one with one radical. We isolate a radical. Now because we have two radicals, we can't isolate both of them, so we just choose one and isolate it. For this equation, the easiest thing to do is to add the square root of x plus 4 to both sides, and that will isolate this radical. So add the square root to both sides and I get this equation. Now I have this radical isolated. But notice this radical is not isolated. My index for this radical is 2, so I square both sides of the equation. Remember what squaring means. Squaring means to take whatever you have and multiply it by itself. On the left side, that just means multiplying the square root by itself. But on the right side, it means multiplying this expression by itself. I need to multiply 1 plus the square root of x plus 4 times 1 plus the square root of x plus 4. That is a FOIL type of multiplication. It is not just 1 squared plus a square root squared. When I square the left-hand side, it just removes the radical and gives me 3x plus 1. When I square the right side, I FOIL. So I'm going to multiply 1 times the square root, multiply 1 times 1 and get 1. Then I'm going to multiply 1 times the square root and get the square root. Then I'm going to multiply the square root times 1 and get the square root. And then I'm going to multiply the square root times itself and get what's underneath. Notice on this side I have 4 terms. You must get 4 terms when you FOIL a binomial. Now simplifying, I can combine my two radical terms. If you remember, if the radicals are exactly alike, I can combine the coefficients in front of them. There is a 1 in front of each of those radicals. There's always a coefficient in front of a variable or a radical. It may not show. If it doesn't show, it's equal to 1. So I have 1 times the square root plus 1 times the square root. 1 plus 1 is 2, and so that gives me 2 times the square root. Two times the square root. I also simplified these other things. I can subtract 1 from both sides, which cancels both of those. That would leave 3x on the left side. I have x plus 4 over here. If I subtract x, I'll have 3x minus x gives 2x. I subtract 4, I get minus 4. Now I have my term with the radical in it isolated. At this point, I can either divide by 2 or I can leave the 2 there and square it at the same time. Either way works fine. In this case, it's a little easier because it divides out evenly to go ahead and divide the 2 and work with something a little simpler. So I divided both sides of the equation by 2. Now, index is 2. I square both sides. Squaring the left side is a FOIL multiplication, so I get 4 terms. Squaring the right side gets rid of the radical. When I collect terms, I get everything on the left-hand side and combine like terms. And when I do that, I wind up with x squared minus 5x equals 0. This was one that the easiest way to solve this equation is to factor it, because the only factoring required is to take out the common factor of x. Then set each factor which contains x, so in other words that and that, set each of those equal to 0 and solve, which gives me x equals 0 and x equals 5. Then, because it's a radical equation, I need to take this 0 and plug it back here and check. I need to take x equals 5, substitute it back there and check. So, checking the 0, plug the 0 into the equation, do the arithmetic, and I get 1 minus 2, which is minus 1. That is not equal to 1. Therefore, 0 does not work, and we must discard it. What about the other one? Let's check 5. Plug 5 in. 4 minus 3 equals 1. 1 does equal 1. So the solution x equals 5 is okay. But we did need to throw away one of our solutions. That is the reason you must do the checking operation. So let's do another one. Same technique. Isolate the radical. Square both sides. Put my equation in standard form so that I can solve it. This one factors. Check my answers. One of them works, one of them doesn't. The 6 works, the minus 2 does not work. So your only solution is 6.